to estimate the performance on weather evolutions.
So we can see from
The graph they are using the root mean square error to measure estimate the performance on weather evolutions.
So we can see from
The graph
Willing, your signal
they
is
are
not very
using
good.
the root mean square error to measure estimate the performance on weather evolutions.
Willing, your signal is not good.
The graph
Willing, your signal is not very good.
the root mean square error to measure estimate.
Oh, we lost the connection. Let me ping Willing.
Hi guys, sorry,
Okay,
because I'm in the library network is not that good. So. Okay, I can share my screen. So we just talked about the performance on the weather evolutions. So they use the root mean square errors, which is right here, this one, and the x tiny reds means they only accept the x as the inputs. Tiny means the tiny training data sets. Red is the red noise, and the S tiny y and S tiny y star have the best performance in terms of the RNSE. So I think this one we can see is very small. So this one RNSE is the lows. This one as well, and this one I think, yes. And about the client evolutions, so some GANs successful to duplicate the true system characteristic, equaling or surpassing the polynomial parameterizing models, but while the other performance poorly. So we can see the true line is kind of like this shape. Oh, they visualize the PDF, or this is the PDF graph. So we can see the true shape like this, but some of the model follow the true shape, but some of them didn't. Is there any question about this result? Okay, great. Oops. Sorry. And the sixth best result is weighted analyze. Weighted is kind of in physical to it's also is a physical and atmosphere combined to estimate how the predictions to measure the atmosphere's models. So we can see except for the SU small white and SU small red, these two lines cannot closely follow the true power curve. This is the true power curve. So only these two models, these two GANs model cannot do very well on the energy evolutions. And by the way, this is the equations for the energy equation. W means the weight. And they also use the mean absolute percentage difference to evaluate the different GANs models. So no GANs performing best across all periods. We only see this the small red GANs. This one have the decreased tendencies. So lower MAPD means the higher the accuracies. And about the discussion, so this study primarily focused the application of GANs in stochastic parameterization. So, which I said before, they offer the framework by directly embed the random C in the model and training process instead of the stochastic after the deterministic parameterizations. But because of the Lorentz 96 system is a simple model, so GANs might overfitting on the data compared to the polynomial parameterization. Lastly is the conclusions. Conclusions said some GANs outperform the benchmark models. So some GANs then did well, did better than the benchmark models. Some GANs with the red nodes produce reliable weather forecasts, which we know the noise is very important, and how to add the noise is very important for predicting the reliable forecasts. Although some GANs, the models are very sensitive to the noise and other hyperparameter settings, they still show the potential for the using in the stochastically parameterized physical process in more complex weather and climate models. That's all for my presentation.
Okay. Any comments?
My comment about the paper?
No, I mean, I'm asking in general, the audience.
No, the audience. Okay.
Anyone of you have additional comments? Okay, great. Yeah, I think these two papers are interesting. And saying that, to me, it's kind of hybrid physics and machine learning model. You're not completely doing data-driven. You're trying to model some terms, partial of the equations as data-driven terms. So there can be a lot of possibilities, and sounds interesting. I don't believe that full data-driven method will dominate everything, right? So if we can introduce proper physics knowledge into the learning procedure, that might achieve the best results, because you can choose the better trade-off. Okay, I think next we'll have Hao Zhe to give the introduction about sequential Monte Carlo. Hao Zhe, are you ready?
Yeah. I'm here, and I want to share my screen.
Yeah, go ahead.
Please wait a minute.
Yeah. So take your time, because we only have less 1 hour. Like we're gonna end around 1.
All right. I want to connect my iPad, but
if you want to connect iPad, I would suggest to first connect your line to connect your iPad to your laptop.
with where? With cable, right? With
connector. Don't use wireless. There are always some problem if you do transfer.
I cannot find the options of the share my iPad.
If you click,
Okay, I will. Oh, all right. Oh, I find it.
yeah, there's one section called iPhone, iPad, wall cable.
All right. Can you see my screen?
Yeah, perfect.
All right. Perfect. All right. Hello everyone. Today I want to introduce the. I want to. Yeah, my name is Hao Zhisuan, and I'm an exchange student in this semester. I'm happy to work with you, and I hope I speak better English. So if you have any problems, please interrupt me, and I will explain it. And today I want to make a presentation about the introduction to the SMC methods. And here is the agent. I want to introduce a method and to point the shortage of this method and to introduce another method and to point the shortage and then we will get a good a fine method. Yeah. And what is the sequential Monte-Carlo method? The sequential Monte-Carlo methods are simulation-based methods for calculating approximations to posterior distributions. They avoid making special assumptions required by related methods such as the Kalman filters. And now I want to make the model formulation. Let the xt denote the sequence of unobserved states, and the yt denote a sequence of observations with yt. And we can define the x0 to t equals x0, x1, x2, blah blah xt, and y1 to t equals y1 blah blah yt. And we make two assumptions. And the first one is xt is a Markov process with initial distribution px0. But it is not needed. It is not necessary. But the authors. But I looked at some books and the authors make these assumptions. But so I make these assumptions here. But it's not needed. But it's not very necessary. And we give xt the observations are conditionally independent. All right. Here we will get two equations, and the first equation is the transition equation, and the second equation is the observation equation. Any problems?
So
Okay.
just to confirm, so you are using this probability structure to illustrate the SMC framework, right? But in general, you don't need to put these assumptions like Markov chain and conditional independence.
Yes. I look a few books and they said it's not necessary. But in the book, the author makes this as the Markov process as the assumptions. So I don't know why it is not needed, because in the next proof, I will use the Markov process. However, the author in the book told me that it's not necessary. That's the problem. So maybe it will make the calculation simple. I don't know.
Oh yeah, just go ahead and introduce. We will try to figure out.
Oh, okay, thank you. And our goal is to estimate the posterior distribution P recursively. We also may care about the marginal distribution P or an expectation such as IHT. It is defined as expectations.
Basically, you want some statistics based on hidden states. Like you want their, for example, their expectation of the summation of hidden states, or expectation of the mean of the average of
Uh,
this, so
yeah,
on.
there is a function ht, and it is xt to the rn to the it is integrable. It may be any functions with respect to the p with to p.
Okay.
Is that make sense? Does it make sense?
Yeah.
Yeah, thank you. All right, and here's we will get the Bayes theorem. The Bayes theorem is yeah, it's a very classical theorem, and I think I do not need to explain it. And now I want to do some proof, do some and we can get these equations because of the PAB equals PAB divided PB, right? And we can find that because it is this one and this one is also because of these equations, right? It is PY equals you can see it equals it, and this one equals this one. Oh, it's too messy. Right, and we can find that this one equals to this one. It is because of this equation,
Yeah.
right?
Yeah.
And the problem is that how do we get this one equals this one? You see, and I think that is because it's a Markov process. The Markov process means that the statement t plus 1 only depends on the state at the time of the t. So we do not need to use the x0, x1, blah blah xt minus 1. It only depends on the xt. So we can get these equations, right? It is because yeah, it's a probability of the xt, the state from the xt to the xt plus 1, and if we get the xt plus 1, the probability of to observe the state of the yt plus 1. Any question?
Okay, so this one can be reduced as the conditional probability of xt plus 1 given xt times yt plus 1 given xt plus 1.
So sorry.
Yeah, I'm just stating the results.
Okay. All right. And we can. And we can get this recursion. It is the same as last slide we get, and now we can get the marginal distribution recursion, and the predicting recursion. It is I think it is it's easy to understand, right? It is because we get the observation of the state y 1 to t minus 1, but now we do not get the observation of the yt, so we can only use the state of the we can only use the state at the time t minus 1 to predict the state of the state at the time of the t. So we get this function. But if we get the state at the t, what happened? Okay, but if we get the state at the yt, we will get this function. It is because the Bayes theorem, it is the same as this one, right? It is I get the state of the observation YT, and we can update the update the state, or update the probability. All right. And now we have solved these questions, because we can use the recursion to solve the probability at any time t. But it's very hard to calculate, because we have the complex high dimensional integrals. So we cannot use these ways to calculate the probability. And now I want to introduce some ways to use the simulation ways to do the to solve the problem. And now I want to introduce the perfect Monte Carlo sampling. It is very unique because in the ideal situation we could draw a sample of size n from P directly. The posterior distribution of interest causes sample. We can form an estimate of P using the empirical distribution of the sample. And this function is called the, it's very famous, it's called the delta Dirac, right? I don't know. Dirac function, it is located at the x0t. It has many interesting property, and yeah, we get these equations, and we can estimate of the IFT using the integrate using this equation.
Yeah, I have a small question. So what's the I means here? What's the I function here? It's a function of the Haydn space.
Sorry?
Yeah, the I function. The I function. So I cannot lost the I function. What's the?
The I function is defined by the it's defined by it. It's a problem we want to solve. It's a expectation.
Yeah, IM means that I use n particles to do the integration.
And then what about the H? It's a utility function?
H is whatever functions we want to apply to the states.
Yeah.
Okay.
We do not. We do not know the HT now. If you can make the HT you want. You can make the HT x0t x0t. Yeah, it's maybe any function you want. All right. And can I continue?
Yeah.
Oh, okay, thank you. And if the variance of INFT if posterior variance satisfies the sigma ft less than the limit, we can get this function. But maybe it's because of the Fermat's theorem, but I do not know how to prove it. I just say the result. And because of the strong law of large numbers, we can get this equation. It means when the n approaches the limits, we can that means if the n approaches the limits, the INFT convergence in distributions as the IFT. And because of the central limit theorem, we can get this function.
Yeah, this is just to tell us that you use particles to approximate the posterior. You got the asymptotic convergence, which has nothing to do with dimension. Yeah, this is knowing results.
Yeah. I just want to show the show these equations. Yeah, and unfortunately, it is usually impossible to sample efficiently from the posterior distribution P at any time t. It is because the P usually non-standard and only know up to proportionally constant. In applied statistics, Markov-Chain mental-color methods are a popular approach to sampling from such complex probability distributions. However, MC methods are not recursive. Not recursive algorithms unsuited to recursive estimation problems. So alternative methods have to be developed. And now we will get the, and now we have the importance sampling. That means that means since we can draw from P directly, we can use importance sampling to draw from P indirectly using an importance sampling density pi and a corresponding importance weight for each draw. The importance sampling density must be chosen so that its support includes the support of P, and we will have IHT equals EHT EHT, and it equals HTX0T PX0T Y1T DX0T, and this one usually equals 1, and we want to do the normalized. And we replace the replace the W for the P, and we will get this equation.
Okay, Haojie, so
Yeah.
you intentionally put a constant 1 in the denominator. That's where you put your weights in both denominator and in both numerator and denominator, right?
Denominator.
Yeah. Look at fraction.
Yeah,
The expectation is just the numerator is fine because denominator must be 1, right? If it is a conditional distribution, right?
Yeah. That's the point. The denominators always will be the 1, and if it is not the 1 and the P is wrong, we need to normalize the P because the P dx always equals 1, right? So we want to approximate the expectation IHT. We simply need to draw a sample from the pi and calculate the IHT. To use this equation, we just okay. Please have a look. It is the same as this equation, this equation, right?
Mhm.
From here.
Yeah.
And if we define the W
W tilde.
W tilde, the W tilde T equals these things, we can get a simple expression, right? And we call the W tilde as a normalized importance weight.
Mm-hmm.
All right, and we will get these equations because of the approximate posterior is given by this, and this is the same as we said like this.
But there's a problem, like you can use that importance width to approximate the integral, right?
Yeah.
But how do you approximate posterior by changing the weight?
We can. Yeah. That is because if we choose a different pi, we have sampling from a density pi. If we have chosen different x from the pi, and we will get a different w.
Oh,
And
I got one. So if we look at this equation, like IHT equals to your HTX 0 to T, W2 to Ti. So x0 to T can be viewed as a set of particles, right? And you can view it as another integral with weighted particles. Their weights are W2 to Ti's.
Yes, that's right.
Okay, so you convert it. Okay, you take an alternating wheel.
Yeah.
And that means you use pi to generate a bunch of particles. Then you evaluate the weights accordingly. You have a set of particles and their weights. You construct approximation of the posterior.
Yes, exactly.
And if you use a different pi to generate a different set of particles, your weights will vary as well.
Yeah, that's right. So we will get different W, and the W2 that we can get the posterior. But the method is not well suited for the recursive problems.
I have a question about how to compute the W. Can you go back to the slide of the how to compute the W? The previous slide. Yeah, so you can compute the pi x0 to T with the denominator, because you know the proposal distribution. How do you compute the denominator?
Do you mean how can I compute these things?
Yes.
That is because it is we know we have the
that's kind of the posterior of the.
Well, is a proportional to some constant normalizer z.
Okay.
When you do a normalize over this W, you can cancel out this normalization constant.
Okay.
Yeah, because actually you won't be able to really compute x, this posterior x0 to T condition on y1 over T. That won't be possible. It must be skewed by some constant. But it's very smart. It's smart in that, Hao-Zhe, can you go to the previous slide?
Yes.
Yeah, the trick here is very important. That means in the second line of the formula, you have to introduce the normalization there. And although it is just one, but you have to put that.
Sure.
Otherwise, you won't be able to normalize your constant W, normalize your W. And you cannot, if you do not normalize your W, there always exists some unknown constant there.
Sorry, I don't understand.
Yeah, the reason is that the whole logic is clear, but the problem is that, okay, you won't be able to really compute this, right? If you're able to compute this, why do you use importance sampling? You don't want to use that. So you construct the weights like this, but eventually you're gonna normalize it, right? You're gonna normalize this, and once you normalize this, you hidden constant z. See, there could be some constant here, and we'll get canceled. I'm not sure if I explain more clear, but actually when you calculate it should be like this. It should be a joint distribution.
Yeah.
Why?
Yeah, I understand.
Yeah, and then divided by some constant, right? If you know this constant z, if you know this normalizer, you don't need to use importance sampling. But the problem is you don't know that. So when you calculate this W, you have no choice. You have to compute the joint distribution rather than this posterior distribution divided by this pi. And then the good thing is that we'll normalize those weights, those constants. This normalizer z will get canceled.
All right. All right. Let's continue. And as I explained the importance of sampling is a general Monte-Carlo integration method. However, in the simplest form, it's not adequate for recursive estimation. That is, one needs to get all the data y before estimating p. In general, each time new data y become available, one needs to recompute the importance weights over the entire state sequence. The computational complexity of this operation increases with time. In the following section, we will introduce a new method to solve this problem, and that is called the sequential importance sampling. The importance sampling method can be modified so that it becomes possible to compute and estimate Pn of P without modifying the past simulated trajectories. This means that the importance function at time t admits, we will get these functions. I'm not sure is it very easy to understand, but I believe
What you write
Yeah,
here is the fact.
sorry.
I mean, what do you write? What do you on the line here? Is the structure of your pi? Because you need to choose a pi, right?
Yeah. Oh, I need to choose the pi in the following. I will introduce the choosing pi in the following slides. And now I want to introduce the property of the pi.
Okay.
We will get these functions. And now I want to show how we can get the
One second, hold on.
Yeah.
So how do you get this property? Since pi x 0 to t given y 1 to t can be decomposed as pi x 0 to t minus 1 given y 1 minus t minus 1.
Sorry.
Okay, so it still assumes some Markov assumption, right? In pi.
Yeah. I know because it is a Markov process, and if we want to get the x 0 to t, we must get x 0 to t minus 1, and so we will get this expression, and we will use this expression to get another state. Maybe I'm not I do
Yeah,
not.
if the pi structure follows your Markov assumption, assuming it's still a Markov chain, and given each x, y are condition independent. Yeah, this is true.
Yeah.
Okay, so you're assuming your importance function also follows this structure, right?
Yes. So I find that in the proof of this method, I need to use the Markov process assumptions. But actually, I have read some books and they also said it's not necessary. I'm not sure. Maybe we can discuss it when I finish.
Yeah, for the formula.
I want to continue with this with Markov process assumptions.
Yeah,浩哲. Oh,
Yeah, I'm here.
yeah. Go back to the previous slide. Yeah, here, the y is this true? Really? Pi x 0. Can it be decomposed pi x 0 times this?
What do you mean pi x 0?
Oh, possible.
Yeah, that's true because it's we just use this recursion and we can get it.
Oh, okay.
You don't have the observation at the first the initial state. So that's a external.
Okay, yeah. Okay. Yeah, go ahead.
All right. We can continue. And I want to show how we can get this. The WT tutor is approximate with WT minus 1 tutor and times this expression. Let's begin. We can the WX0T is equals the PS0T Y1T and pi X0T Y1T, right? And we will know that the X0T Y0T
Yeah.
It's too long. It's too long. It is because these things and we can get this from here, right?
Yeah.
And we can continue, and we will get the Px0T minus 1 Y1T1 times PXTYT X0T minus 1 Y
Minus 1, yeah.
and it's really long. It's a very complicated proof. So it is because of the I think this part is very easy to understand. It is because of this part, right? You can see it. We can we can get it from this part, and for this part. And for this part, we can get it from this part. Yeah, it's very easy to understand, and I just照抄就把这一部分抄下来，就 sorry, all right, we can understand it and we can continue. And we will get the P S0 T1 1 we will use this part. Oh, sorry, no. Oh, yes, we will use. We will use this part and this part to get this part, and this part and this part. So we will have this part. So we will have this part and this part and this part, right? And we just put it here, and we can get the P, Y, T, S, T, P, P, X, T, S0, T minus 1, and get the P, Y, T, Y1, T1, pi, S, T, 0, TG, Y1, T. All right. All right. We can get these things. We can get these things, and this thing is equals W tilde T plus T minus 1I, and this thing is a little complicated, but we have found that this one is but this term is constant for all x. Is only, oh no, is only contains the, it only contains the y and no x. So we can consult it, and now we will get this. And now we will get these equations. This WT tilde is approximate to the WT minus 1 tilde and 2 times this equation, right? And if you do not understand, if I do not approve it clearly, we can discuss it after the meeting. Yeah. All right. And we will find a special case occurs when the pi equals to the px0t, and it equals the px0 and minus p minus these things, and it will resulting in the W, and we replace the P to this one. We replace P to this equation, and we will get the W is approximate to the W times P, and we will get this relationships.
Oh, so the case that you're gonna use the prior over x, you just remove y. You just assume y1 to t has nothing to do with x. It's just the chain of x.
Yeah.
Okay.
Yeah. That's right. And we will find that SRS is usually inefficient for high dimensional integrals, because as t approaches to the limits, the importance weights for some particles quickly approach 0.
Can you go back one slide? I just want to look at how everything is cancelled.
This slide.
Oh, okay. Yeah. Then the p xti given xt minus I will be cancelled. Also the denominator. Denominator will be exactly p xti given xt minus I.
Yeah. That's right. If we use this pi, we will get these two things cancel out.
Okay. Okay.
That's my code. All right, we will get these two things cancel out, and we will.
Okay.
Yeah, right. And we have some issues with this method because of the if the t approaches to the limits, the importance width for some particles quickly approach zero, and we will get only only a few non-zero importance weight if the t is big enough. So we want to use the bootstrap filter to solve this problem. The key idea of the bootstrap filter is to eliminate the particles having low importance with WT tilde, and to multiply particles having high importance weights. More formally, we replace the weighted empirical distributions by the unweighted measure. It is a uniformly weighted distributions Pn, and in the post slides we can find that and it's the weighted, and it's the weighted distribution. We replace these things for the Pn, right? And we will find the most common invoice resampling n times from Pn. And I want to the Ni is the number of offspring of the particle xi. And if the Ni equals 0, the particle x dies. And now we want to find a good method. We want to find a good method to select the n. And there are many different ways to select the nt. No city, it's a mistake. There are many different ways to select the NTI, and the most popular becoming the one introduced in the Gordon this article, and here one obtains the surviving particles by sampling n times from the distribution Pn. This is equivalent to sampling the number of offspring NTI. It is a mistake. And NTI according to it is a temple, no city. According to a multinomial distribution of parameters WT tilde. If you ask me why, I do not know. Is another paper, and I haven't read it, but
so let me summarize the idea. So the idea is that, okay, I'm going to use current particles and their weights.
Yeah.
So just to resample those particles. Some of particles will never appear. We just remove it.
Yeah. That is because if the function is like this, if we use too many theses approach 0, and we will and when the t approaches the limits, the width will become 0, and we cannot use the computer to calculate them because it's very hard, because so we want to cancel these particles and make them more focused on this non-zero area. And I have pictures to show this. The first we have 10 particles, and we give them a weighted, and the more weighted particles will get more n. And then we resampling, and now we resampling this this N to the we resampling these particles to get a new WT, and we repeat it, and we will get the distributions right.
Oh, so the particles itself can be,
Oh,
the value could be
Yeah.
the same, but they are gonna in a subsequent procedure, they still have a chance to be assigned different weights.
Yeah, that's right.
Oh,
And
okay.
and I want to show the algorithm. Initial we draw x0 from the px0, and there are many particles, and we can do the importance sampling step. And for the I from 1 to n, we draw a new XTI from the PXT STI and set this into this and set them into this set. And we will recalculate the WT and normalize it. And now we will do the resampling step. We will take n draws with replacement of the original x2 and with width. If their width is too low, we will kick them out, and and set the t equals t plus 1 and repeated the important sampling step and the resampling step. And
so after the resampling procedures, all the particles has the same weights.
After the resampling step, what?
They have the all the particles have the uniform weights, or
Yeah, they should have the same weights. It becomes 1 over n again.
Yeah.
But these particles can have the same value, but they're treated as different particles. But because you're doing the chain, right? Because even two particles, their values are the same at current state, and we'll move to the next stage, like t plus 1, because you're gonna draw a new state to append to that. So in general, the trajectory can still, bifurcate to generate new trajectories.
But I feel it's a bit weird. I do not understand. If we calculate if we kick this out, how can we approach the right distribution? Actually, I do not.
It's not a kick out. It's like you got you approximate the distribution, right? You use your mass point distribution. It's a multinomial distribution, right? You have different weights for those particles. Now you just generate samples from that distribution. You didn't change the distribution. Like, yeah, for example, you got like multinomial distribution, like say you got 10 possible particles. Each particle, they have a different weights. 1 over half, like 1 over fifth, something like that, right? You got 10 such probabilities. You're going to run multinomial distribution for n times, or you're going to generate samples from this multinomial distribution, but it doesn't necessarily that you have sample every possible value in this 10 possible items. But your samples are still rigorously follow your multinomial distribution. It doesn't change the distribution. It's a smart idea, because like it's like, okay, I'm gonna start with many trajectories, and now at some stage, I'm gonna collapse, right? Because I'm gonna pick up those with larger chance, larger probability trajectories. The others, when you do the resampling, it might be just killed, right? And for example, this one will be shared, and now you got next state to generate another two trajectories, but they share the past trajectory. And you might generate a bunch of new trajectories and go along for a while. And then some low probability paths will be kicked out as well. And then based upon that, you're gonna generate new particles. And to generate new trajectories, but these new trajectories will share some part of old trajectories as well.
All right.
Yeah, I think we can. I think we can discuss a little bit more. But you do have introduced the content, right?
Yeah. I have finished it. And
Okay, perfect. Yeah, very good slides. Is the LaTeX done by you?
Yeah. It's I made this LaTeX by the Overleaf.
Oh, cool.
It's a fantastic tools to make LaTeX. I think because it's very convenient. I do not need to to get the right the environment to care about the environment, to care about the package. I just open it and use it. Yeah.
Okay, perfect. That's very good. Yeah. I think we need to stop here today, but this is very useful because we got quite a few words based on those filtering. We're using common filtering, RTS smoothing to do several works. It's mainly Shikai's work, but we have never thought about like using sequential Monte Carlo of doing this, right? So, but in general, sequential Monte Carlo is symptotically convergent to the true posterior. We don't need to make additional determinist approximation about posterior. So I think it's very useful. And in general, sequential Monte Carlo is not only useful for like simulating Markov chain, right? Simulating a state space model, we actually can use it to train any probabilistic model. But anyway, I think we can spend a bit more time to discuss in our next seminar. And yeah, thanks, Haozhe. And yeah, let's stop here today. So Haozhe and Wenling, can you send your slides to Shibo?
Okay.
And they will probably Shibo will release it in our group seminar webpage. And also,
do you need the source code?
No, just
no,
PDF.
just the PDF. Yeah. PDF will be sufficient. Yeah. Okay. Thanks, everyone. Yeah.
Okay. Thank you. Goodbye.
Bye.